In our last lab, we calculated the coefficient of friction by dragging objects across the workbench. It wasn't the most accurate results because we had two challenges. One was that we had to drag the object carefully by hand and try to go at the exact same speed all the way across the bench. And the second challenge we had was we had to read our Newton scale while doing so. And it was challenging to do, especially since some objects weren't very heavy. What we're going to do in this lab is we're going to do it the same project, but we're going to do it a little more precisely, a little more accurately by using what's known as a Fletcher machine. First off, you're going to need a pulley, some weights, and some string. So what we want is we want to have this pulley so it's sticking up above the workbench. So obviously putting it on this way wouldn't work because it's underneath the bench. So make sure we get it on correctly. So we're going to put it on and then we'll screw it on with the screw handle to make sure it's snug. Then what we're going to do is take a piece of string and we're going to have the string so that it goes over the pulley like so. So you want a string about 1.5 to 2 meters long. And what you're going to do in each end of the string is make a little loop with a knot to hold them in place. Next, what we're going to do is we're going to take our small weights, doesn't have to be the smallest one, but just take a little weight, hook it on the end, and then that'll hold it as we secure the weight over the end of our pulley. I'll come back to that in a moment. Please note that with our weights, they are sort of stackable here. So what I can do is I can hook one weight to the other and make a little chain of them. Okay, so please note that we can have a whole stack of weights here if we so choose. So once again, I've got my small weight hooked onto the end of my string. I'm going to dangle the string over the pulley at the end. And then at the other end of the string, I'm going to hook it onto the block. What we're going to do is we're going to calculate the coefficient of friction between this wooden block and my work desk. Okay? The weight was just enough to hold it in place. If the weight's too heavy, if I had to use the big weight, then obviously what would happen is that the whole thing would come crashing down. And I don't want that. I just want to hold it in place so the string stays in place. Okay, so right now what we have is we have friction holding my block in place where it is. And what we want to do is we want to have this block slide down the work desk, okay? But we don't want it accelerating. We want this to go at a nice, constant, slow speed. How do we do that? Well, I've got a weight attached over the corner of the pulley. And we'll talk more about that in a brief minute. So what we need to do is we need to increase the weights on the end so that the block moves. Let's try this one. Well, that one's obviously way too heavy. So I know that it's less than 200 grams. I'm going to try 50 grams. Still doesn't want to move. Okay, so it's more than 50, less than 200. I'm going to add a little bit more. Still not going. Now I'm getting close. And what you should see is, remember that our static friction is more than our kinetic friction. So sometimes what I'm going to do is I'm just going to give it a little nudge with my finger here. I'm going to move my camera up a little bit. I'm just going to give it a little nudge. And it's still stopping. So friction is still too strong. So I need a little more weight. Oh, we're pretty close. Really close. So I'm going to repeat this process until when I give it a nudge, it just slides at a nice uniform speed. I'm really close that time. Okay, so a couple things go wrong in this experiment. Let's just get those out of the way so you know what they are. First of all, we're going to make the assumption that the pulley right in here has no friction. Unfortunately, everything has friction. They're pretty small friction, but we're gonna make an assumption that there is zero friction in the pulley. The second big assumption is we're going to assume that the string has no weight. The string does have weight, it's small, but the problem is that if it has weight, as it pulls and goes over the corner, the amount of weight on the top compared to the amount of weight hanging down the side changes, and that's a calculus kind of problem, and we're not quite ready to worry about that. So we're going to assume that it is a weightless string. The third thing we want to try to do, and we can fix this one pretty well, is we want to make sure that the string is horizontal to the surface of the desk. And when I look at this one, you'll see that, hopefully you can see it, is that I can't really change the height of my pulley. I can make it a little higher, but I can't make it any lower. That's as low as this pulley goes. But you can see that my cart is actually a little bit downhill. Ideally, I need to find a way to raise that up so that this is parallel to the surface. The other thing I want to do is I want to make sure that the surface of my workbench is flat and level. We're going to make that assumption that it is. You don't need to get out the tools and measure for level. But what we want is we want that cart being pulled with a string that's parallel to the floor, that's perfectly level. So I've drawn my workbench here in black, and I've got my cart here in blue, and this blue here is the string going over the pulley and down, and I've got a weight in the little cart here, the wooden block, and I got another weight hanging off the end of the bench here. Okay, and I've recorded my masses. So I put it on the scale, and I saw that the mass of the cart plus any weights was 0.361 kilograms. I also measured the mass of the piece hanging off the end, and it was 50 grams or 0.05 kilograms. I calculated the weight of both caused by gravity, and I have my answers here. So the next thing we need to do is figure out the vectors that are involved. So what we've determined is that there's a force of gravity on this cart of 3.54 newtons. So that's the force of gravity on the cart, which means that we have an equal and opposite force, known as our normal force, which is 3.54 newtons, and that's upward. What we have is we have friction, and friction is in the opposite direction of the accelerated force or the applied force, as I like to call it. Okay? What we know is that if the cart stays at a constant speed, there is no acceleration. And if there's no acceleration, that means that F net is zero. No acceleration, F net is zero. And for that to happen, our force of friction must equal our applied force. So if we could figure out our applied force, we would know that it's equal in magnitude, opposite in direction of our frictional force. And our applied force is quite simple. It's how hard were we pulling on the string? Well, all that the pulley does is the pulley just changes direction. It doesn't change our force. If this is a frictionless pulley, it does not slow anything down. It just changes the direction of our force. So from this problem, our applied force, our FA, is the same thing as the gravitational force of the second weight. So our FA here would be 0.4905 newtons. And that then tells us that the force of friction on this problem is 0.4905 newtons. So we previously learned that the coefficient of friction, mu, is equal to the ratio of the frictional force to the normal force. So in this problem, we know that the frictional force was 0.4905 newtons. And we will now compare that to our force of gravity, or our normal force, I should say, which is 3.54 newtons. We have calculated that mu for this example is 0.13855. So in this experiment, you're going to work in pairs, and each pair is going to pass in an answer. And you're going to, at the end, you're going to pass in 5 different trials plus a graph. 5 trials plus a graph. Now, what you're going to do is you're going to use the exact same block. You're going to use the exact same surface every time. But what you're going to do is you're going to use weights in the block. You're going to add some of the masses that we have. And so you might do it with the block empty, and then you might put 100 grams in the block, and then maybe 200 grams in the block, or 500 grams in the block. And then you need to find which weight on it to get it to pull it over the edge just ever so slightly, and calculate the coefficient of friction for each of your 5 trials. So each pair is going to pass in 5 trials. Then what you're going to do is you're going to put your results into a data table and graph it. I'm curious to see, will there be any relationship between the mass of the block and the weights compared to the weights hanging over the side, and compared to the coefficient of friction. So that's what we're going to do. When we're done, we're going to create a data table of our 5 masses of the cart and our coefficients of friction that we calculated. And then what we're going to do is put that into a scatter plot graph and see, does it make a straight line or a curve, exponential, logarithmic? What kind of function does this make?